The write-up lands on a Wednesday and it is not about a stolen password. The intruder reached one small internal service of yours, and from there read every other service you own. Nothing was cracked and nothing was forged. Every one of those services simply answered, because the request arrived from inside the network, and being inside was the only credential any of them asked for. That is the quiet kind of failure that costs you a quarter and costs your users their trust. So what did each of those services check before it answered? Not who was calling. Only that somebody could reach it. Hold that question about what got checked, because the next quarter hour turns on it, and we will come back to it at the very end. Here is the sentence you have written in a design document, or nodded along to in a review without turning it over. We use TLS, so traffic between our services is encrypted, and encrypted means secure. Simple. But that is not a mechanism, it is a mood. Encryption tells you a stranger on the wire cannot read your bytes. Does it tell you who is at the other end? It tells you something, and it is worth being precise about how little. Ordinary TLS is one-sided by design, and that is deliberate. The server sends you a certificate, your client checks it against a list of authorities you already trust, confirms the name on it matches the name you dialed, and then you agree on keys. So you learn which server you reached. What does that server learn about you? Nothing at all. Your handshake never asked. Let us try that definition again, because TLS in both directions is where most explanations stop. Mutual TLS means your client presents a certificate too. True, and still furniture rather than physics. It tells you which flag to set. Does it tell you what new fact your server holds? It does not, and that fact is the entire point. So let us build the thing instead of naming it, and watch your system grow until it needs this. Say you run the internal shipping platform called Dockline. Version 1 is a single service behind one Jinx ingress, and the only thing talking to it is a web page. Your TLS ends at Jinx, everything behind it is plain HTTP on a private subnet, and that is fine, because there is nothing behind it but one process. Then you split Dockline, the way these things go. A rating service, a label service, a tracking service, a billing service, all calling each other. How does your label service know the call on its port is really your rating service? Version 2 answers with a shared secret. Every service gets one API key in its environment, and the receiver compares strings. Watch what happens as you grow. That key is in a Kubernetes secret, and a continuous integration variable, and on a laptop, and pasted into a chat thread from the night somebody was debugging at home. Where exactly does your key live now? You cannot answer that, and you cannot rotate it without a coordinated deploy across every service at once, so you never do. Note, a shared secret proves membership, not identity. If every Dockline service holds the same key, your key answers is this one of us and can never answer which one of us. So one intruder who reads your rating services environment becomes all four of your services at the same moment, which is precisely the story you opened with. Version 3 stops comparing strings and starts checking signatures. You give every Dockline workload its own certificate and private key. That certificate is a short signed document saying this public key belongs to the label service, and the private key never leaves the process that owns it. You share nothing, so there is nothing to copy out of one place and reuse everywhere. Now your handshake changes shape. Your server sends its certificate as before, then a certificate request, which is the polite way of saying your turn. Your client sends its own chain back, signs a transcript of the conversation so far with its private key, and your server verifies that signature with the public key inside the certificate it just received. Notice what that last step buys you, because it is the part people skip. A certificate is public. Anybody can copy one out of a packet capture, so presenting one proves nothing by itself. Signing a transcript that exists only inside this handshake proves possession of the matching private key, and possession is what nobody can lift out of your log file. Which gives you a definition worth keeping, and it has 3 clauses. Mutual TLS is a handshake where both sides present a certificate, both prove possession of the matching private key, and both validate the other side's certificate against a trust anchor you configured in advance. All of it finishes before one byte of your application protocol is sent. Take that last clause seriously, because it is your practical difference. The check happens beneath your code, so your request handler never runs for a caller that failed it. Compare that with a token in a header, which reaches you only after you parsed a request and routed it somewhere that might forget to look. Note, the current version, TLS 1.3, standardized by the IETF as request for comments 8446, moved the certificate exchange after the keys are agreed. So your certificates are encrypted on the wire, and a passive observer cannot see which of your workloads is calling which. The older version sent them in the clear, so the version on your proxies is not cosmetic. Where does your trust anchor come from? Not from the public web. The authorities baked into your browser exist to vouch for domain names to strangers. Dockline needs to vouch for its own workloads to itself, so you run one internal certificate authority, and configure every service to trust exactly that authority and nothing else. Case in point, Kubernetes has shipped this pattern for years. Its control plane components authenticate to each other with client certificates from a cluster authority, and the kubelet on every node does the same. HashiCorp Vault issues short-lived certificates on demand. The Cert Manager project automates renewal. AWS Private Certificate Authority sells the authority as a managed service, and Cloudflare does the client certificate check at its edge. How short is short? Public web certificates are measured in months, and the industry is arguing about whether 90 days is already too long. Your internal workload certificates are measured in hours. 24 hours is common, and meshes routinely go below it, because a certificate that expires by itself is a credential you never have to remember to revoke. Pull on that, because revocation is the oldest sore spot in this field. The classical answers are a revocation list your client is supposed to download, and one online status check your client is supposed to make. Both add a network dependency to your fast path, and both fail in the direction of allowing the call. Which does your service consult today? Your honest answer is probably neither. So the modern move is to make revocation unnecessary rather than fast. Issue for 1 hour, and a key stolen from you is worthless by lunchtime. You have not solved revocation. You traded it for expiry, which happens on its own without you remembering to make it happen. Analogy, think of a festival wristband rather than a permanent membership card. Nobody keeps a list of cancelled wristbands, because it is only good for today and tomorrow the color changes. What that costs you is somebody handing out fresh ones every day, and in your system that somebody is automation that can break. Which is why this arrived as infrastructure rather than library code. Envoy runs beside each of your workloads as a sidecar proxy and terminates the connection, so your application opens a plain socket and the proxy does the certificate work. Istio and Linkerd are the control planes that configure fleets of those proxies and rotate their keys underneath you. Note, identity in a mesh needs a name, and a name shaped like a domain is wrong for a workload. The SPIF project standardized a uniform resource identifier for exactly this, so your Dockline certificate carries a path naming its trust domain, namespace, and service account instead of a host name. That is what lets you write policy about workloads rather than addresses. So what does your receiving service actually get out of all this? A verified name. Not a permission, not a role, not a user. Which brings a boundary into focus that a lot of your designs will blur. Mutual TLS authenticates the caller. It does not authorize the call. Knowing the connection genuinely is your label service does not tell you whether it may issue refunds. That decision still lives in policy above the transport, and it is a second system with its own set of mistakes in it. The other boundary surprises people. A workload certificate says which service is calling, and nothing about which human is behind the call. If somebody signs into your Dockline and their request fans out across 4 services, the certificate on each hop identifies the hop, and you still need something else to carry the user. In practice, that is a signed token alongside, so mutual TLS does not replace your token work. It sits underneath and makes your token harder to steal. Notice the pattern in both. The property is real, and narrower than its name suggests. So your useful question is never do we have mutual TLS, it is which exact claim am I leaning on, and did any of my code check it? Now the failure modes, and almost none are cryptographic. The first is verifying the chain and forgetting the name. Your server requires a client certificate signed by your Dockline authority, and stops there. But every Dockline workload holds one signed by that same authority. So your billing service now accepts a connection from your tracking service and treats it as anything at all, because nothing compared the name on it against the callers your endpoint expects. Authentication without a name check is a doorman who inspects the seal on your invitation and never reads it. The second is terminating in the wrong place. Your load balancer accepts the client certificate, verifies it properly, then opens a fresh plain connection to your service, because that is the default shape of a reverse proxy. The property you paid for stops at your edge. Some proxies forward the verified identity in a header, which helps, and also means your service now trusts a header, the very thing you were stopping. The third is expiry, and it is why this technology has the reputation it has with you. A 24-hour certificate is a daily deadline. If your renewal path breaks quietly on a public holiday, your whole fleet stops talking to itself at the same minute, and you will read it as a total outage rather than one broken job. That is the trade-off you sign for, and it cannot be argued away. Every hour you shave off the lifetime, you shave off your own margin for a renewal that did not run. Note, clocks matter more here than anywhere else in your stack. A certificate is valid between two timestamps, so one of your nodes with a clock a few minutes adrift will reject certificates every neighbor accepts. In practice, treat a drifting clock as one outage with a date on it you have not reached yet. The fourth is trusting far too many authorities. If your client library falls back to the operating system trust store, any authority in there can mint a certificate your service accepts, and there are hundreds of them. Your internal traffic does not need any of that reach, so pin one authority explicitly. Which store is your client reading right now? That is worth 10 minutes of yours today rather than a paragraph in a review later. The fifth is the escape hatch, and it ships in every library you use. There is a flag that turns verification off. It has a reasonable sounding name, and it exists because somebody needed a self-signed certificate to work on a laptop before stand-up. OpenSSL connects without verifying anything if you ask it that way, and so does your HTTP client. Search your repository for that flag and read every hit, because the ones in your tests are harmless and the ones in your deployment manifest are a hole. Quick win, pick one of your internal services and run the handshake by hand from a shell. OpenSSL shows you the chain your server sends, whether it asks for a client certificate at all, and what it does when you offer none. In practice, 2 minutes of that tells you more than a whole day reading configuration files. So here is where two systems genuinely diverge, and your divergence is a choice rather than a mistake. One company decides the network is the boundary, firewalls, private subnets, and a bearer token for anything crossing the building line. The other decides the workload is the boundary, and authenticates every call no matter which cable it traveled down. The first is cheaper on the day you build it, and degrades in a specific way. It sits exactly one mistake away from a flat internal network, and your mistake is usually a stray route or a compromised pod. The second costs you something every day, and degrades differently. It fails loudly, on a schedule, when a certificate does not renew, and it very rarely fails silently. Which of those failure shapes would you rather debug? That is a real question, and your answer depends on how many services you own. Case in point, Google published its own version of this argument as BeyondCorp, and the summary is that a perimeter stops being useful once both your service count and your network count keep growing. Which is why the honest recommendation is not turn this on everywhere tonight. If your Dockline is 3 services in one cluster owned by one team, mutual TLS may not be worth the effort, and one well-guarded boundary with short-lived tokens will still require less of your attention than a certificate pipeline. If your Dockline is 40 services across 3 clusters, your boundary story stopped being true long before you noticed, and you will still require some way to answer the question you opened with. Which brings you back to that question. What did each of your internal services check before it answered? Reachability, and nothing else. That is the whole of it. Every service trusted your network trusted anybody already inside, so the first foothold was also the last one your intruder ever needed. Mutual TLS is not a product you buy, and it is not encryption you switch on. It is your decision to move that one check out of the network and into the connection, so who is calling has one answer that does not depend at all on where the call came from. So take these to your own architecture and answer them without opening a document. Does anything behind your ingress verify the caller, or only that the caller arrived? If somebody read one service's file system tonight, how many of your other services would they instantly become? Where does your outermost certificate check happen, and does the connection behind it carry any identity? How long do your internal credentials live, and who would find out if renewal stopped? And the one that decides the rest, how many services do you have, and is that number still going up? Ask yourself those 5, and if 4 make you want to go and check something, that is your answer about where the next quarter should go. It might well be that a smaller, sharper boundary is the right choice for the system you actually have rather than the one on the diagram. Decide for yourself, and decide it on the shape of the failure you are willing to debug at 3 in the morning, not on the strength of the acronym.